Hi class, welcome back to Electromagnetics. So with this lecture we're going to start the next part of this course, which will be part 4. So the thought for the day is do not, Zechariah 4:10, do not despise these small beginnings, for the Lord rejoices to see the work begin. So I thought that was appropriate today because this will kind of be a short lecture because we're just starting to set up the groundwork for analyzing the propagation of electromagnetic waves. And so we'll be doing a very small part today, setting up the current sheet. So with that, I think it's important. I think the Lord indicates here that, we don't need to despise small beginnings. Sometimes that's the hardest part, is just to start the work or begin the work. I know at least that's true for me. So I think that was kind of the gist of the thought for the day that I was thinking. So as I said, part 4, wave propagation in free space. Again, 6 little mini lectures as we've been doing. The first one today, we're going to set up the infinite plane current sheet. So with our new understanding of Maxwell's equations and their application to electromagnetic waves, we see that there is an interdependence between space variation of electromagnetic field components related to the time variation of the complement of that, the magnetic and electric field, respectively. So as the electric field at a certain location, the way it behaves is dependent on the time variation of the magnetic field and vice versa. So this interdependence of electric and magnetic fields then gives rise to a phenomena that we call electromagnetic wave propagation. And so we want to take a look at that now. So to begin our study of this subject, we're going to start, like I said, with a very simple special case that it's going to be purely hypothetical, but with this, it's going to help us understand and build on these principles to move forward with real life applications. So the jump from this hypothetical to real life, we'll see later in the course, is not a huge jump. It's still pretty applicable with a few adjustments. So the special case that we're going to look at is what we call uniform plane waves. And so this is defined as a wave that's going to be propagating, we're going to say in the z direction, but you're going to have these electric field components and these magnetic field components that are going to be orthogonal to that. So they are actually going back and forth as they go down the z-axis, so it kind of gives the appearance that it's transmitting or propagating down the z-axis. And so we're going to define these components of this wave as just an E field, which just has an X component, but it is going to vary along Z and with time. And then we're going to have this H component going this way on the Y-axis. It's only going to have a Y component. And again, it also varies with Z as it moves down the Z-axis and time. So to create this hypothetical wave, we must first define a hypothetical source. So this source we'll consider will be an infinite sheet lying in the xy plane. And so it looks something like this. So we're looking at just the xy plane, so we have this sheet, infinite sheet, taking up the entire plane. So on this infinite sheet, we'll define a uniformly distributed current varying sinusoidally with time in the negative x direction. So it's going up and down in the x direction in a sinusoidal pattern. So since this current is distributed on a surface, then it might make a little more sense to talk about this as a current density, right? And so we'll define this current density as some maximum magnitude times the sinusoidal component here, which will have a frequency and it's dependent on time in the x direction. And then this only occurs at z equals 0. It doesn't occur anywhere else along the z-axis. So if we now define a width in this xy plane that is parallel to the y-axis, which you can see represented here, just some arbitrary width here, the current crossing that width then will just be the width times the current density. So you'll just have a negative W, which is our width, times our maximum amplitude of a current density times the sinusoidal component of that. So the graph of the time history of this current would then look something like this at that point, or on that width. Just so you can see it's maximum negative amplitude going to 0 and then increasing to the positive maximum amplitude and so on and so forth. So it is sinusoidal.